Buckle up, folks, because today we're taking a deep dive into the mysterious world of dark energy. And get this, we've got not one, but two new research papers that are really shaking things up.
Oh, yeah, this is exciting stuff.
The first one throws a curveball right off the bat with this wild idea of dark energy radiation. Have you heard about this?
It's like, imagine a faint hum of energy, this constant sort of background noise permeating the entire universe. That's dark energy radiation, or DER for short.
Okay, so we've already got dark matter and the cosmic microwave background out there. How is this DER different?
Well, that's the thing. It's a totally different beast. See, DER is made up of particles, but it's not like the usual suspects. And what's really wild is that it could be way more abundant than we ever thought, like 1,000 times more.
Hold on a second. 1,000 times. Shouldn't we have noticed all that extra energy before if it's that common?
Well, that's the really clever part. It's not like DR has just been sitting around since the Big Bang, see? It's actually what we call dynamically produced, meaning it's been gradually increasing over time.
So it's like a cosmic snowball effect.
Exactly. It starts small, but as the universe expands, DR just keeps growing and growing. And because it's a gradual process, it's only now that we're starting to see its effects on a cosmic scale.
That is so cool. So how do we actually go about detecting this elusive DR? I mean, if it's this invisible force, how do we even begin to study it?
Well, it's tricky, right? But the paper suggests looking for its fingerprints, so to speak, on other particles like neutrinos, axions, and those ever so mysterious dark photons.
So we're looking for clues for how DR affects things we can detect.
Exactly. It's like cosmic detective work. If these particles interact with DER, they get a little energy boost, and that's what we're trying to find, that subtle energy signature.
What would those signatures even look like? What are we looking for specifically?
Well, for starters, there's the Ptolemy project, which is already looking for neutrinos, but they're specifically looking for interactions with tritium. To find a DR-boosted neutrino, though, we'd need some seriously next-level precision.
Wow. What are those other particles? Axions. Are those on the table too?
Axions are interesting. Most of the current experiments are geared towards finding them in the context of dark matter, right? But DER suggests we might need to be looking at different energies. It's like it's opening up a whole new avenue for these experiments.
DER is shaking things up.
Yeah.
So axions are a possibility, and then there's dark photons.
And dark photons. Well, that's where things get really exciting. There's an experiment called LIDARA that's specifically designed to hunt for those. If DER is indeed boosting those dark photons, LIDARA could be our key to unlocking this whole hidden energy field.
So even though we haven't directly seen it yet, all this research suggests that DER could be leaving its mark all over the universe, and we're getting closer to connecting those dots.
Exactly. It's like we're piecing together this massive cosmic puzzle, and DER might just be that missing piece that helps us see the bigger picture.
I love it. Okay, but get this. We're not done with the mind-bending discoveries just yet. This next paper takes aim at how the structure of the universe itself might be throwing a wrench into our whole understanding of dark energy. And trust me, it's a wild ride. This next paper comes to us from Italy, and they're tackling this really cool question about how the structure of the universe itself might be messing with our understanding of dark energy.
Yeah, it's a good one.
So before we get into the nitty-gritty, can you kind of set the stage for us? How could the way the universe is structured even play a role in how we understand something as fundamental as dark energy?
Well, it all comes down to challenging our assumptions, right? Like, we often think of the universe as this smooth, uniformly expanding thing, kind of like a perfectly round balloon that just keeps inflating.
Yeah, that makes sense. I mean, it's kind of the classic analogy, right?
Right. But in reality, the universe is a lot more complex than that. It's not smooth at all. It's actually pretty clumpy. Like, picture a giant cosmic web with these dense clusters of galaxies, all connected by these filaments of matter.
Okay, so more like a spider web than a balloon.
That's exact. And here's the really wild part. All that lumpiness, all those massive structures, they actually warp the fabric of space-time itself.
Whoa, okay, things are getting a little trippy now. But I'm still not quite following. How does warp space-time play into all of this?
Okay, so imagine you're trying to measure the Earth, right? But the ruler you're using, it's all bendy and distorted. You're not going to get a very accurate measurement, are you?
Good point.
That's kind of what's happening with dark energy. We use this concept called area distance to measure distances across the universe. It's based on how bright or faint objects appear. But these Italian researchers, they're suggesting that the lumpiness of space-time caused by those massive galaxy clusters could actually be throwing off our area distance measurements.
So it's like our cosmic ruler is a bit wonky,
Hmm.
and that's messing with how we understand dark energy. Okay, I think I'm starting to get it.
Exactly. And get this, their calculations suggest that at the edges of galaxy clusters, where you have this transition zone between areas that are gravitationally bound and areas expanding with the universe, the lumpy space-time effect, it could actually mimic the signal of dark energy itself.
Wait, are you serious? You're saying that what we think is dark energy, this mysterious force pushing the universe apart, could actually be a side effect of how these massive structures are warping space-time.
It's a pretty wild idea, right? And look, it's still early days. A lot more research needs to be done, but their findings are definitely throwing a wrench into our cosmic understanding.
No kidding. It's like we thought we were looking at this mysterious force, but maybe it's just the universe playing tricks on us with its weird, lumpy structure. I love it. This is why I love these deep dives. We are uncovering some serious cosmic plot twists here. All right, so let's try and recap all of this because we've covered some seriously mind-bending stuff today, haven't we?
Yeah, no kidding.
First, we had dark energy radiation, DER, potentially more abundant than we ever imagined. And now this idea that the structure of the universe itself might be throwing off our whole understanding of dark energy.
It really makes you question everything we thought we knew, you
Yeah.
know? Like, it really highlights just how much we still don't understand about the universe.
No kidding. So much for dark energy being this one simple thing, right?
Right, it's not just one thing. It's this complex web of interactions and influences.
Which is pretty cool when you think about it. And you know what's really interesting to me is how these two papers, even though they seem like separate ideas, might actually be connected.
Oh, yeah. How so?
Well, on one hand, you've got DER,
Hmm?
potentially becoming more influential as the universe ages, right?
Right, like a snowball effect.
Exactly. And then on the other hand, we have these massive structures, these galaxy clusters, warping space-time and potentially skewing our measurements of dark energy. So what happens when you throw those two ideas together?
Well, you start to wonder, right? Like, if dark energy is affected by how space-time is structured, and that structure is constantly evolving as the universe expands, then could dark energy itself be changing over time?
Whoa, that is a huge question.
It is.
Because then it's not just about how much dark energy there is, it's about how it's changing and evolving along with the universe itself.
Exactly. And suddenly we have to rethink everything. How do we even begin to measure something like that?
Right. We might need a whole new set of tools and observations to even wrap our heads around that.
We might, but that's the beauty of it, right? These papers aren't just theoretical, they're giving us concrete things to look for.
Exactly. Whether it's searching for those subtle energy boosts from DER or figuring out new ways to measure how galaxy clusters are warping space-time, it feels like we're on the verge of a whole new chapter in our understanding of the universe.
Absolutely.
And for all of you listening, here's a final thought to ponder. If dark energy is indeed changing over time, what does that mean for the fate of the universe? Will it keep expanding forever, or is something else entirely in store for us? One thing's for sure, the universe is full of surprises. And we'll be back again soon to dive into more of them right here on The Deep Dive.